Thank you very much. Thank you for inviting me to Elat. I'm just gonna sort of jump right into it. We, as architects, we have to not only design beautiful buildings and expressive sculptures, but we need to think about and design ecosystems, ecosystems of flow of energy through our buildings and our cities. So when we work, we sort of in our work we have started this new way of thinking where we try to include. It's not a new way of thinking, but in our office at least, we have now our own engineering department, our product department, and a landscape department. And the name for this lecture today is called formgivning, which is the Danish word for giving form, because we as architects need to give form to something that has not yet been conceived. So literally giving form to the future. Big is a company based in 3 locations. I already got it. We have, this is a little old, but we have 550 people in those 3 locations. And our buildings are spread all over the world. And this is some office with some very dedicated staff in both Copenhagen and our office in Copenhagen, where we sit in this old factory. The recent years we completed quite a bunch of projects, and we have a number of projects coming up in the next couple of years, and I'm gonna explain a little bit more about what is happening here with these projects. So it all sort of started in Denmark, where we got the job to build some housing, some very inexpensive housing projects. This is the V house. After that came the Mountain, which was a combination between a parking structure and 80 penthouse apartments on top that used the parking as almost like a foundation for the apartments. Underneath you have this almost like cathedral of car culture nested under the mountain. The third project was the 8 house, which is all the way in the same part of town in Copenhagen. This figure 8 building that is, instead of a traditional city where you put the different buildings next to each other, it's layered as a pancake with penthouses and sort of a walkway that takes you from ground floor all the way to the 10th floor. And then we just finished Noma, the world's or former world's best restaurant in Copenhagen. They have got a new, very sort of organic place in the outskirts of Copenhagen. Also last year we finished the Lego headquarters or experience center in another part of Denmark, where both kids and adults can sort of enjoy the splendors of playing with Lego. We moved to New York and started our office there. One of the bigger projects is the Google headquarters that we are currently. This is a month-old image, but it's this very big canopy that covers a completely open and flexible working environment that can be sort of inhabited in all types of ways. The roof is covered with PV panels, and you have these open windows in the roof that takes daylight into the working environment. Then all of the office went to this great experiment in the Nevada desert, Burning Man, which is an annual city that grows from nothing and stays there for 1 week, and then it disappears again. And this is almost like a giant outdoor museum with over 2,000 art pieces in the desert. And we brought this giant sphere that is 500 times of 500 times the size of 500,000 times the size of Earth. It's 25.5 meters in diameter, and it sort of hovers over the playa and sort of reflects the environment around. This is a ballet that was occurring under the orb, as we call it, during that week. So it all started when we sort of became really international, when we moved to New York and introduced this building that we call the Court Scraper, which essentially is this warped pyramid that, unlike all the other buildings, because it has this shape, reflects the light from the sky, and therefore in the sort of the early mornings or late evenings, it's sort of the only building that stands out really in the New York skyline. It's located on West 57th Street, close to Central Park, all the way to the Hudson River. And Denmark or Europe is sort of very well known for our courtyard buildings that sort of have this semi-private common space in the center, almost like a green lawn where you can get away from the city life and relax. In a similar way, Central Park has the same. It's the same kind of a green lawn that protects the citizens, or so they can get out into nature. And we thought we wanted to introduce the courtyard building to a New York context. So the idea was to merge the typical New York skyscraper sitting on a podium of amenity with the courtyard building. The starting point was simply laying out the courtyard building and then dragging up the northern corner as high as we could get, and this would allow sun to shine into all apartments on the northern side, but also give abundance of daylight to the courtyard itself. From in here, the people living in the building would also have a great view of the surrounding nature. So here's sort of a fly-through of the building from inside the courtyard, where you have this protected little private lawn with green patches, a view from one of the apartments out onto the Hudson River, and because the roof dips down in all the way to the park, everyone inside the courtyard actually has a view out. The lobby space, and here from down where you see how this saddle-shaped roof works out. And when you get to a distance from the building, it sort of rises and becomes a part of the skyline in New York. We are also we finished a project last year that's called Urban Rigger. It's this idea of creating a fully self-sustainable little housing complex, if you will, that can be sailed around to any locations in the world. So the Urban Rigger is essentially like a concrete base with 12 housing units on top, and they're made out of shipping containers that are stacked on top of each other. So the little house comes together and forms like a community. And if you start placing the urban riggers next to each other, you can create an entire neighborhood. So you have the concrete pontoon at the bottom, 9 containers stacked on top of each other, and a little bit of steel holding everything together. And here, the 12 units can sort of enjoy everyday life in their own little courtyard. The building is sort of one big ecosystem itself. It has PV panels on the roof that drives some pumps that essentially pulls water through the base of the pontoon so that you can extract the heat from the water, and that is used to heat up the units in the winter times, but it can also cool down the units in the summertime. And if one boat is having a party, they can sort of connect to each other and borrow electricity from each other. So it becomes this sort of system that can expand almost forever. So this is a project we're doing in Sweden, in Gothenburg, where we are connecting this old harbor area into a little neighborhood with 32 units. Here are some of the images from the Danish harbor, where we have one. We are placing, or we have 5 more in production in China that will be shipped to Copenhagen when they're ready. And of course, there's a little ladder so you can go swim directly from your own house. Inside, you have a protected courtyard with glass screens, so on windy days, it's still a calm area in the center. And then from in there, you are directly in connection with water in these 12 small units. Sort of, these are fitted as student housing. But essentially it could be anything from galleries, restaurants, libraries, and so on. Then from here, it's right now parked in Copenhagen Harbor. In the backside, you see our man-made mountain arc. The project is one of a few power plants that we have in Copenhagen that burn trash into electricity. In Denmark, it's over half of the trash we have that are burned and turned into electricity and heat. We have 42% that are recycled, and only 4% are placed on landfill. The power plant is located right next to sort of the center of Copenhagen city. This is seen from one of the spires of the old churches in downtown Copenhagen. If you look at trash as a resource, 3 kilos of household trash is you can extract 4 hours of electricity for a household and 5 hours of district heating. So in a sense, it's a very sort of valuable resource. 1 ton of trash is almost 2 barrels of oil. This is what power plants like this normally looks like. These sort of big boxes, very alien to people. You see the old power plant in the background. It's sitting right next in the sort of the heart of Copenhagen and one of the marinas, next to some go-kart. You have water skiing, and we thought when we have such a big building, there was an opportunity because people happily go skiing to Sweden and other places, because Denmark is flat as a pancake. We don't have any mountains, but we have mountains of trash in the form of a power plant. So our idea was to sort of import a Swedish ski resort and cover the entire building with this hill. So we reorganized the interior of the power plant into sort of this sloping side and covered it in a big facade and placed a green park on the roof of this. In the corner we have an elevator that can take you up to the roof that allows you to ski on a black, a blue and a green piste. So this is what it looks like in the greater context. The power plant is now finished and in operation, and they're installing this artificial ski slope material. But in wintertime, when we have snow, we can of course ski there. And in summertime, you'll be walking in this big park, complete with ski lifts and everything around, and people skiing on this green carpet of artificial ski slope material. So this will be all year round skiing in Copenhagen from the beginning of next year. And as sort of a final gesture, when we designed the project, we wanted to have this idea of making people aware of the size of pollution, because none of us know what a ton of CO2 is. It's this intangible thing, and if you don't know, then you cannot act. So the idea was to create this mechanism that sits on top of the smokestack, that every time a ton of CO2 has been burned and emitted out through the chimney, we would blow a giant smoke ring so that the inhabitants of Copenhagen could look at the smokestack and see how often these smoke rings comes out of the chimney. And of course, if suddenly it starts happening faster and faster, it would encourage people to start recycling more. So we did a test in Copenhagen of this mechanism out in a couple of years ago now, and it's just to show the enthusiasm of trying to solve these related architectural questions. So the smoke ring is actually made out of steam, because the only thing visible in smoke is essentially the water vapor but the power plant is so clean that it filters out all water and particles in the smoke, so the smoke is almost invisible. So we are instead using the steam that is produced in the power plant to blow this giant, so it's a completely clean and non-toxic steam ring that we're blowing out. So as architects, we often find ourselves in this situation where we try to tackle challenges that lie beyond a traditional scope of work for designers and architects. And this was sort of an example of that. So a couple of years ago, and this was sort of the start of a division that we call Big Ideas within our office. And Big Ideas has been sort of tackling different challenges within our office, and one of them being this new form of transportation that essentially is Hyperloop, which is a high-speed transportation at close to the speed of sound, 1,200 kilometers an hour. And we were asked, it's a company based in LA, and we were asked to look at a route between Dubai and Abu Dhabi as the first sort of case study. But if you look at transportation, this is a logarithmic scale and the sort of speed. So Hyperloop ranks higher than traditional airplanes, so you can get faster from A to B, and they can be located right in the city centers. So this would be a great opportunity to really cut down transportation time, and it takes sort of all the advantages of sort of shipping a lot of cargo from A to B, and combining it with sort of the autonomous freedom of the car and the mass transportation potential of train with the speed of flight. And it sort of gives us the opportunity to look at this new paradigm shift within transportation, that potentially we could create something that could get us from A to B at a much faster pace. Elon Musk came out with this a few years back because now we have the technology to do this. Because it's not an old idea. It's been tested in London and in New York. There was one in New York that worked for 1 year, but simply because of the mechanical challenges, the time these things broke down pretty quickly. But now we are in an age where robotics and very precise manufacturing techniques, we are able to do this. And essentially, it's a tube where you suck out all the air, so you have no air resistance. This is the same reason why planes fly high. They fly high to avoid air. But here, because you suck out the air, you can then put a maglev train or similar into the tube, and you can accelerate it, and it will not stop because there's nothing to break it down. So that's sort of the principle behind it. Hyperloop One have then been testing in the desert of Nevada, and they've been looking at different routes all over the world. And the first one we were asked to is the one in Dubai. I just, for fun, last night did a test on their website to check what the distance or the travel time between Tel Aviv and Haifa would be. So that's to city center 11 minutes, which I guess Eilat to Tel Aviv would be almost equivalent. It's just to compare, and you always think that flight is fast, but you need to check in, and especially here with a high level of security, that might take a little bit of time, so you end up always traveling for a lot of time when you fly. But with a Hyperloop, this could completely change this. So the first route that we were asked to look at as a sort of a case study, and there's been many right now. The most potential one is in India, between Pune and Mumbai, that we're working on at the moment. And there's also one in Scandinavia, Copenhagen, Stockholm, Helsinki, and in the US. But the one I'm showing you here is the only one that is public, so that's the one I can show you. And essentially, this route would also be around 11 minutes from A to B. And the sort of the greater advantages of the Middle East is that you have a lot of open land, and it's not that difficult if you need to dig it down. The ground is often sandy compared to Finland, where the ground is granite, so it requires a bit more. So the Middle East is actually quite a good place to start. Could be Tel Aviv to Haifa or Jerusalem or something. But our idea was essentially to create this system that was in sort of the long-term vision a point-to-point. So from your house door to your house door, and you never needed to change means of transportation. You would order a Hyperloop pod that would bring you all the way into the system and all the way to your destination. So the little pod could essentially be fitted in different ways and combined with other pods, even cargo, placed into this airplane vessel, if you will, the container that shields for the outside vacuum that you have in the tube. This is the tube that surrounds it, and then that would then propel you from A to B anywhere in the world in the future. So essentially you have a direction one of the other ways, and the parts are spaced with 9 seconds apart, which at that speed means that they are very, very far away from each other. Then essentially you make a little loop on the tubes where you place the stations, and here the transporters would then offload the little pods that would park out in the Hyperloop portal, the station as we call it, where people could get out, but also the pods themselves could leave the portal and get into the city. So the first station was here in Abu Dhabi, a big ring that also acted as a bridge over this busy street and connected sort of the corners of the site. In Dubai, or you could say in Etihad, at the Etihad Towers, it was a big ring. At Burj Khalifa in Dubai, it was more like a curled up place, this disc that was tilted, placed on a little plaza. So it's not much bigger than a metro station or similar, and could be placed anywhere in cities. And this is sort of the vision for the Hyperloop. So a guy at work. So here all the parts can be collected from the entire neighborhood into one of those transporters. That is the vessel that keeps the vacuum out, if you will. And then essentially you can propel it to very, very high speeds, and in principle there's no upper limit to the speed. It can go faster than the speed of sound, but that's sort of what they are talking about at the moment. Inside, because it's floating on magnets and maglets, it can be completely still, no shaking. And then 10 minutes later he arrives in Dubai. And instead of getting out on the station, his pod leaves the station or the portal and takes him right to his destination in the city. So, of course, this is a pretty sort of futuristic idea, but this tube is in Vegas. It's 500 meters long. And Hyperloop 1 have been testing this for quite a while now. And on the stretch of 500 meters, they have accelerated this pod up to 460 kilometers an hour in 500 meters. So it's a very, very, that's sort of as far as they could reach. It goes into near vacuum, where the magnets that sit under the pod accelerates the pod up to 460 kilometers an hour. So this was sort of a full system test where all of what is needed to do this was tested in the system. And what is also interesting is the sound, because there is no air in there, so the sound cannot travel. So that's the sound of the future. So of course, the idea at the time was that would be the first stretch, and it could expand out even to all the way to Israel and further up to Europe, all the way around to Russia and so on. And eventually the idea, and possibly also some of the reasons why Elon Musk proposed it, is that on other planets where you have no air, this would be the ideal form of transportation so that's why we included the little moon. But that takes me to another planet in our solar system, Mars. And we were asked to look at what buildings on Mars would look like. In order to design what's called the Mars City, that was going to be a research center located in Dubai. But in order to do so, we had to sort of look at why do you actually want to go to Mars. I'm going to take you through a little bit of a history lesson in spaceflight. So of course, people have been traveling all the time. A lot of the times it was, or in the early times, it was due to sort of natural occurring events like ice melting and so on. At a point, we sort of started developing different kind of tools, like the boat, the wheel, horse, and so on, that would allow us to travel further and further. And then we developed navigation tools, compasses, telescopes, and eventually our phones with Google Maps and so forth that would allow us to get from A to B in the most direct routes. As I said, in the early days, when people started sort of migrating, it was because of inventions. So when humans invented fire, they were able to keep warm when they moved to colder regions, and when the ice melted, they were able to get even further north, but also with the help of the boat they could conquer Australia. And ice melting again would allow us to inhabit the north, where I come from, and sort of so these bigger natural events had sort of led us to eventually conquer the entire planet and reach the remote islands on this globe. We traveled on horses across Europe. That was a 3-month journey through the entire Roman Empire. The Magellan expedition went from south tip of Spain to South America in a 6-month journey. The Trans-Siberian Highway is a 4-week journey in the early days. 60 years ago, if we wanted to visit Australia from Northern Europe, you would have to stop over a lot of times to refuel. So that would also take 2 to 3 days to get down there. This year, British Airways opened a route from London to Australia, and that is one direct route. And Elon Musk proposed to use his rockets to send us from across the globe in less than 40 minutes. Back in '69, we visited the moon. It took us 2.5 days to get there, and altogether the trip was an 8-day journey. And the trips to Mars we are proposing should take 3 months, but if you look back in history, it's not very uncommon for us to travel for months. This is what we used to do. We are just used now to travel from that a trip around the globe would take a day or so. So in a way, we have always been traveling for months to get somewhere. And previously it was big oceans of water. Now it's just oceans of space. So why go to Mars? Mars is our closest neighbor in the solar system, and it actually contains a lot of the things you need in order to sustain life. There's a lot of carbon, water, metallic resources. There's a challenge with radiation on the planet, but you can deal with that. It has a day cycle geothermal energy, so you can, and it has an atmosphere, and it's actually a reasonable travel distance, where some of the other planets are further out and has more sort of challenges that we need to overcome. So on Earth, we have a 24-hour day cycle. Mars is very, very similar to that, 24 hours and 40 minutes. So it would be very humans would adapt very easily. And this is not just something that planets are. In fact, if you look at Mercury, it has a day cycle of 175 days. So it means you would have night for 175 days if you would visit Mercury. And Uranus is orbiting the Sun at this almost like a 90-degree tilt, and it takes 42 years to circle Earth, which means that you have a 21-year-long winter. And so you don't really want to be on the backside here for 21 years in darkness. So just to say that Mars is actually very similar to Earth in many ways. If you look at the landmass on Earth compared to the landmass of Mars, if you extract all the water, it's quite similar in size of Earth. Earth has a protective magnetic field that protects us from cosmic radiation. Mars doesn't have an iron core, so it doesn't create this. So we need ways of dealing with this. If you look at an image of Earth taken from high altitude and compare it to Mars, you see the blue line up here, which is the atmosphere. And this is the atmosphere of Mars. So it also has a sort of something protecting Martians for radiation. This is a sunset on Earth, a sunset on Mars, where the sunsets are actually blue due to the particles in the air. So Earth and Mars has this strange sister-brother hood. Of course, humans has been going to Mars for many years now, and some of them, the later ones, this is the Mars Reconnaissance Orbiter, has been taking these amazing photos of Mars that sort of reveals what an incredible place it would be to go. This was a crater. Here's some lava flows that comes out of the interior, some rock slides formation down these dunes in the landscape, ice around the poles, polar caps. You find these ice fields. This is a dust devil blowing across the Martian surface, captured live on the from the orbiter circling. Here's a landslide again down or an avalanche down one of the sides of one of the mountains. Old river flows on the surface of Mars. And then, of course, we have our Curiosity rovers that's been bringing us amazing materials of the landscape that you find on Mars. These beautiful sort of rock formations and mountains that future people could explore if they would go there. See these amazing canyons through the landscape. And last week there was another satellite landing on the surface, the InSight, which is going to measure what's inside the planet with a very sensitive equipment and figure out things like if we dig down and create underground habitats, what would that, can we do that? Is there too many small quakes that will destroy our homes? But of course, Mars has a lot of good things, but there are also some challenging things that we need to tackle. Roald Amundsen was an explorer that went from Northern Europe to America, and compared to other explorers, they went in big ships and brought all their food with them. and so on. But Roald Amundsen, he only brought himself, and he learned to live like the Eskimos. So he learned to capture seals and so on. And he made it all the way to America, whereas the other ships, a lot of them failed and froze in, and the horses died and so on. So Robert Zubrin, a very well-known writer about Mars, he proposes that we should do like Roald Amundsen. We should go to Mars because it's very expensive to send goods to Mars. So we should first bring all the necessary equipment in order to settle on Mars. Then we should bring machines that can build our buildings. And finally, we should bring nothing on the planet. Even though Mars looks like a very desolate place, we actually have everything we need. So from the Martian soil, we can sort of put it through this regolith treatment plant, and from that we can extract ice. And ice, as you know, is water. We can take the bigger stones and create and fine sand. So we can create bricks. We can create Martian concrete using the water, and we can create ceramics. We can further extract from the fine sand different minerals like aluminum, silica, and create glass, so that we can produce our own electronics up there, and essentially create the base for our technology and our knowledge. But we can also produce photovoltaic panels so that we can get energy from the sun. With electrolysis and the energy, we can create oxygen, so we can breathe, and hydrogen. And combined with the Martian atmosphere, which is primarily CO2, through a reactor, we can create methane. And methane is a wonderful rocket propellant, so we can get back again to planet Earth. We can also, together with carbon monoxide, or create carbon monoxide from this reaction, so we can create steel. And through a chemical reaction, we can create hard plastics, so we can create fiberglass and furniture, bottles, etc. We can also create soft plastics like textiles, tires, ropes. And of course, all of the materials that we produce on Mars would go into a big ecosystem. We could then create our transparent plastics, which essentially would be our domes that we could place on the planet. In the water, we grow our plants and create a root zone cleaning system so that we constantly have clean water up there that we can use to create our recreational areas, but also grow our food, create our food, and essentially sustain life on planet Mars. So a bit like this gentleman that captured these plants in a bottle 60 years ago, and he didn't open the bottle once, and these plants has been growing for 60 years only with the help from the sun. These plants have been thriving in a closed ecosystem. And when we go to Mars, we also need to create a closed ecosystem. As a starting point, we would need some inflatable structures that can capture the air, but they're not good for a number of things. For example, the radiation, as I described before. Inside these domes, we can 3D print structures. Again, the structures don't solve all the problems, and we can dig under the ground to protect ourselves for the radiation while we sleep. So if you combine those three techniques, digging underground, building on top of the ground with the domes, we actually have a sustainable system where you at night, when you're sleeping most of the time, are protected. And that means that you can actually spend out here on the surface 4 hours a day with sort of your spacesuit on, but then the rest of the time you have to be inside the buildings because these different layers sort of protect you for different kind of sort of levels of protection. So essentially that could become your future homes of domes that could be connected together you have these in-between zones that would both act as safety and redundancy for the domes, and you could keep expanding. So the first project, this was for Mars. The first one was in Dubai, in this park outside the city center, where we would build the first dome here. And once that would be built, we would have some 3D printing robots that would create our homes inside. And then we would have robots, meanwhile, that would dig out for the next couple of domes in the neighbors. And eventually, we'd create the whole environment that would be the Mars Science City. That would have people from all over the world coming in, learning about Mars and space. And you then walk through these small, narrow streets that protect you from the harsh sun from above. On Mars, it would protect you from radiation. And inside the buildings, water is actually a very good absorbent for radiation. So you could have these only a 1 meter layer of skylight of water would protect you 100%, and you could then look out and get the daylight into your Martian home on top of the buildings. You have lush gardens. And of course, in the research center, we would study a lot of technologies that would all relate to Mars, and sort of learning centers and so forth. So I have a little quick movie. You see, I'm running out of time. I just have one final note. So if all goes well, we'll start. Thank you. We'll start building this project next year in January. And of course, you may ask, why do we want to go to Mars? And there's some very good reasons why we, of course, should do that. Humans have always been explorers in technology, and amongst the sustainable goals of the UN, a lot of them can be directly related to all the challenges that we are going to face if we move to Mars. So by studying Mars, we also learn a lot about how to tackle our own challenges at home on the planet, like drinking water, creating pure drinking water, energy production, and so forth. So by solving the challenges, because you need to do that for Mars and create small closed ecosystems, you also solve a lot of the challenges that we're facing right now on planet Earth. And the final image I'm going to show, this is an image taken from the Apollo mission on the moon, back at planet Earth. And this is the Curiosity rover looking back, seeing this little blue dot in the distance, and that is Earth. Thank you.